Okay, when we last left, we were talking about capacitors and capacitors with dielectrics. And so I just kind of want to go through that concept one more time really quickly. When you have a capacitor, without a dielectric, you're going to set up an electric field between the two parallel plates. But then if you put a piece of plastic or some other type of dielectric in here with charges that can rotate but not necessarily conduct, in other words, transfer from one plate to another, you get this polarization inside. And so what happens is you get an electric field inside the dielectric that goes up instead of down. And so the net, because you now have some electric field going down, oops, that was the wrong color, because you have some electric field going down, the original electric field, and you have a new electric field that competes with it going up, you're basically knocking down the overall electric field, so you have less electric field. And with less electric field, there's less potential, and it'll be easier for charges to begin to accumulate. So we say the capacitance will increase because you have less V. The smaller the V, the larger the C. So if you have less V for the same geometry, then you can put more Q up here. So that's the idea. All right, moving on. One of the concepts we want to talk about today is energy stored in a capacitor. This is a kind of a neat little look at old-fashioned type of capacitors. But if you can imagine with the capacitor, and I mentioned before that if you first add charge, adding the first charges is pretty easy because there isn't much repulsion from nearby charges. But if you add more and more charges, it gets harder and harder to add the next one. So now I have a little charge and I want to put on, it's going to take me more and more work to do it. Every time I add a charge, it gets harder for the next charge to be added. So we can actually use calculus to kind of calculate how much work would be done in the process of charging up a capacitor. And so here are the solutions to our little integral. We're going to integrate the work over time. And just for fun, I created some slides to show you the math behind that for those of you who are calculus types and are curious. Just for you non-calculus, don't worry about it. But the idea is I've reversed the order, but V is going to equal Q over C. So if in an intermediate stage you have like a little voltage is going to be a little charge over the capacitor. So we're going to integrate, have a little chunk of work is going to be V dq. We're going to integrate the work, and so I'll let you look at it and figure out and follow along. But basically the solution to the integral is this Q squared over 2C. So that's one way of representing the total energy stored. That's all the work that gets put into charging up a capacitor. Now we can express that in different ways by doing some simple substitution. So we know that C is equal to Q over V, which means Q is equal to CV. So I'm going to take that CV and plug it in over here where I saw that Q squared, and I will get CV squared over 2. So that becomes another way to express the energy. And then finally, we can substitute one more time and say, well, 1 over C is V over Q. So I'm going to plug in, I'm going to plug that in for the Q squared. Q squared over TC could be written as V over Q times Q squared over 2. And then you can cancel that out and get QV over 2. So there's 3 different expressions that all represent the energy stored up in a capacitor, and the one that you choose depends on the information you have, like what do you know is being held constant, the charge or the voltage or the capacitance or what, depending on the problem. So you'll get to play with that with your homework problems. All right. So the work to charge up a capacitor is going to be equal to the energy that's stored in the capacitor and available for discharge. So for example, with a flash bulb or with a defibrillator, you charge it up and then you can discharge it. One thing that's interesting to note is that for a sphere, we know that electric potential is going to be K times Q over R, where Q is the charge of the sphere, divided by the radius. So if you think about capacitance, which is Q over V, then we can take the V term from over here. We can take that V term from over here, plug this in down below, and then rearrange, and we get R over K. Well, that's kind of interesting. The capacitance for a spherical capacitor is the radius divided by K. Now, that means if you have a really large radius, you're going to have a really high capacitance. And that's one of the reasons that the Earth has such a great source of charges. It's like a giant capacitor. It has lots and lots of charges. Lots and lots of charges available for us to use when we want to ground something. All right, charging capacitor. I mentioned this briefly, but if you connect a battery to a capacitor, it will charge the capacitor to the same voltage as the battery. So, for example, if you have a 12-volt battery, you're going to get a capacitor up to 12 volts as well. So, for example, if we have a capacitance that has 12 nanofarads, and I want to know what's the charge going to be, if you know the voltage and you know the capacitance, you can just calculate the charge. So in this case, I got a total of 1.4 times 10 to the negative 7th coulombs. All right. Defibrillator, I mentioned that a second ago, is just basically a capacitor. So you have two little pads and you put them on either side of your heart. And the idea is you want to jumpstart your heart, get it back into an electrical kind of a sinus rhythm. And so you do that by passing some current right through the tissue. So you put the pads on either side, and then you say that whole clear thing is let the shock, let the current flow. So what is the charge if you have a capacitance of a defibrillator is about 50 microfarads and about 5,000 volts? How much charge are you talking about? Again, you can just capacitance is charge over voltage, and you can solve and find that the total charge is going to be about 0.25 coulombs. And that doesn't sound like a lot, but that is a heck of a lot. That's a lot of current flowing through your heart. And this is just a really fun image of a capacitor, also known as a ho-ho, but you get the idea. You have your dielectric in here, and then you have the metal on the outside, and you can roll it up. So you can form a capacitor by rolling up a dielectric inside a metal. Okay, finally, concept questions. I think I talked about these before, but let's just go over again. As you move from the center to the surface of a positively charged conducting sphere, the electric potential will stay the same. Because the electric field is 0 inside a conductor, the potential is the same everywhere, so it will not be changing. And the next one, as the charge of two capacitor plates doubles, the potential difference between the plates will have to do what? Well, again, if you start with a capacitor and you have a little bit of charge on it, you're going to set up an electric field. If you now double the charge, that is my cat freaking out. If you now double the charge, you're going to have twice the electric field. If you have twice the electric field, you're going to have twice the voltage. So this capacitance, it keeps the ratio between the charge and the voltage. So if you double the charge, you're going to double the voltage, as long as you don't exceed the maximum capacity for the capacitor. Every capacitor has a set voltage beyond which it will break down. We say it's a dielectric breakdown, and it will basically melt the material and create a little short circuit. So at some point, you can't add any more charge, or you'll end up destroying your capacitor. So the answer was doubled. If the distance between two charged capacitor plates is tripled while the capacitor is disconnected from the battery, the voltage between the plates will do what? This one is actually not that easy to think about. So I'm going to break it down and say, well, if you disconnect something from a battery, you need to know that no more charge is allowed to flow to go onto the plates. So the Q is going to be the same. Now, if you increase the separation, because the capacitance is proportional to 1 over D, if you triple the D, that is going to decrease your capacitance. So you're going to have 1/3 the capacitance you had before. And if that's the case, then if you have to multiply the left side by 1/3, you're going to have to multiply the right side by 1/3. But you know that Q doesn't change because you've disconnected the battery, which means that the voltage must. So you're going to get the voltage times 3, or 3 times the voltage. And you might think conceptually, why is that? Well, think about having two parallel plates with a positive and a negative charge, and you're holding on to them. They're pretty close together. They want to get really close together because they're oppositely charged. So you're basically holding them apart. Now, if you separate them more, you have to work to separate them. So basically, by pulling them apart, you are putting in energy to do it. You are increasing the potential between these two plates because they would rather be together. So how much potential? Well, if you triple the distance, you're going to triple the potential energy, and therefore the potential. Okay, so the answer is increased by 3 times. And finally, a charged parallel plate capacitor originally has air between the plates. If it remains connected to a battery, while a piece of plastic is put between the plates, the charge will do what? Now, if you have a battery connected to a capacitor and you do something, you leave the battery attached, that means that flow, charge is going to be able to go in or out. But if the battery stays connected, that means the voltage is going to stay the same. So the question is, what's going to happen to the charge? Right? So if you have a dielectric, then your overall electric field is going to shrink because of that polarization of the dielectric material. So you have less electric field, which means you're going to have less voltage, I guess, potential between the two. If the voltage would tend to go down, that means the capacitance is going to go up. So we know that because the capacitance goes up when you put in a dielectric, if you actually hold the voltage the same by having the battery stay attached, this case would be if you were to detach it, but by having the battery stay attached, when you have an increase in capacitance, you're going to get more charge coming on board. So the answer is the charge will increase. And that concludes our lecture for today.